the driving force behind the OpenCog architecture, among many other things, and is primarily based at the Polytechnic University of Hong Kong at the moment. He is also the mind between the AI company Novamenti and several other enterprises. And I think the next two talks will be primarily concerned with cognitive architecture OpenCog.
Thanks, Joseph. Yeah, I'm going to give two brief talks on different aspects of the overall OpenCog AGI project, and then one of my colleagues will give a third talk on yet another aspect of OpenCog. If you want an overall overview of the OpenCog project, you can look at opencog.org. Basically, these talks are based on 3 conference papers from the proceedings, each of which looks at a little part of what we're doing in the OpenCog project. This first talk covers the integration of vision processing with abstract cognition, which is something that's very much still a work in progress. And the second part covers pattern recognition of the data that comes out of sensory processing, which is something that's a little more mature. So part 1, we'll talk about combining symbolic and subsymbolic processing and some of the interesting issues that we've been wrestling there within OpenCog. And this is more a report of some ongoing work than a grand presentation of results and conclusions. I mean, the first thing I would say is the dichotomy of symbolic versus subsymbolic, while historically important in the AI field, doesn't necessarily make a lot of sense. I mean, the algorithms that are thought of as subsymbolic, like recurrent neural nets, have been proven able to do a lot of symbolic processing, not just in theory, but in practice, using recurrent backprop and various standard learning algorithms. On the other hand, while logic-based AI systems have often been used in a purely symbolic way on rule files and so forth, there's no reason you can't hook a logic engine up to a camera and actuators, and there's been some work on things like that. So the dichotomy in its extreme form doesn't exist. On the other hand, it does seem to be true that some algorithms and approaches excel at some things, others excel at others, and I mean, no one has done theorem proving or language parsing as well with a neural net or a GA as they've done with a logic system, and no one has done vision processing as well with a logic engine as they've done with a hierarchical neural net. So I think it does make sense to talk about integrating symbolic and subsymbolic components in an integrative cognitive architecture. And one way to do that we've been taking in the OpenCog system is take a subsymbolic system and use it basically as a perception module. Use some pattern mining algorithms to recognize patterns in the states of the perception system. Then have your symbolic reasoning system act on those patterns that are recognized within the states of the perception system. And then you can have some feedback too. Use your symbolic system to bias the subsymbolic system to recognize certain kinds of patterns. And in terms of the high-level architecture of the mind, and this is a very crude diagram that's borrowed from Aaron Sloman's COGAF, meta-architecture in essence, which is just kind of textbook cognitive psychology. But in terms of this kind of architecture, what I'm talking about here is sort of at the interface between perception subsystems and then a whole bunch of other stuff in the mind, working memory, long-term memory, reaction, deliberation, metacognition, and so forth. So, somewhat less crude view of what we're talking about. A subsymbolic architecture of the type we're working with here is we're looking at hierarchical temporal memory type architectures, which I refer to by the ugly acronym CSDLN, the Compositional Spatial Temporal Deep Learning Network. And Jeff Hawkins' HTM is probably the best known such architecture. We've been working with Itamar Arel's DeSTIN architecture, which is qualitatively similar in nature, but with different mathematics. And we've been looking at how do you bridge between a network like that, which sort of sub-symbolically and hierarchically recognizes patterns in its inputs. How do you bridge that with something like OpenCog, which in its most transparent aspect is more like a symbolic semantic network. So, for example, the DeSTIN or HTM network recognizes things coming in through an artificial retina. And so it will recognize the precise geometric aspect of a face presented to it or something. But how about the more general conceptual nature of a face, like two eyes next to each other, kind of a nose below it, where even if you stretch it in a weird way, a human will still recognize it as a face. So there's some recognition of the more abstract patterns amongst the elements of the image. And we embody that by having a pattern mining system recognize more abstract patterns in the set of states of the sub-symbolic pattern recognition engine. The more abstract patterns, such as, oh, there are these two kind of ovalish things that tend to be next to each other. That sort of more abstract pattern is extracted by a pattern mining engine and put into the OpenCog network. So I'll now briefly review the two components being integrated in the experiment I'll describe here. One being the OpenCog engine, which is a humongous software system and cognitive architecture. The other being the DeSTIN visual pattern recognition system. So OpenCog, it's a big system, and I reviewed it in like a 2-hour tutorial session at the AGI conference last year. I'm not going to try to summarize it well in 2 minutes here, but we have subsystems corresponding to many different kinds of memory: declarative, procedural, episodic, sensory, motor, attention, goals. And we have different learning algorithms associated with these different kinds of memory, which are all designed to hopefully work well and cooperatively with each other. We've been using OpenCog largely to control virtual agents in virtual worlds. We're now dabbling with robots as well. Many of these ideas are described in a book I published in 2006 called The Hidden Pattern, which is a more conceptual philosophy of mind type of book. And next year, my 1,000-page, I can't quite call it a magnum opus, except in the literal sense. It's a big book, which is what those words mean in Latin. But my big book describing the OpenCog architecture should come out next year, called Building Better Minds. And the key aspect that will be important for this talk, OpenCog's knowledge representation, it's a weighted labeled hypergraph, so it's nodes and links. Some of them have an explicit semantic representation, some of them are more sub-symbolic, analogous to nodes and links in an attractor neural net, such as a Hopfield net. So we have both explicit knowledge representation, where you could have nodes and links that essentially encompass logic relations in a semantic net type form, and implicit knowledge representation, where knowledge can be expressed as patterns of activity across a large number of nodes. And both of these occur in the same network, which is not that hard to work out. We've been doing that since the mid-1990s. But this sort of weighted labeled semantic network type representation is quite different than what you have in a sub-symbolic hierarchical pattern recognition network. And how to bridge the gap between those two has been interesting to think about. A key notion in OpenCog has been the concept of cognitive synergy, which is a fancy term for something pretty obvious, which means that we have different learning mechanisms corresponding to different kinds of memory. We use a probabilistic logic engine to handle declarative knowledge. We use an evolutionary programming engine to learn procedures. For sensory knowledge, we use this hierarchical pattern recognition stuff I'll talk about now. For attentional knowledge, spreading of attention, we use something kind of like a Hopfield network, but it's based on theoretical economics, so it sends artificial money around between the nodes in the network. All these different algorithms, they're supposed to work together to help each other overcome the combinatorial explosions to which they would otherwise be susceptible. Now, the extent to which the theoretical synergy among these processes manifests itself in reality is something we're still exploring. It's a large system. And the two biggest AI components here you could read about separately. The probabilistic logic engine is in a book from Springer a few years ago, Probabilistic Logic Networks. Procedure learning is handled by the Moses probabilistic evolutionary learning algorithm, which is from Moshe Lutz's 2006 PhD thesis from Washington University at metacog.org. I mean, each of those is actually a big story unto itself that I'm not going to tell now. I'm a super AGI optimist, unlike many of our speakers that we've heard earlier, and I'm of the belief, together with my collaborator David Hansen, we could create human-level thinking machines within a decade or less if sufficient funding were put into it to get enough minds and put on the problem and pushing straight toward the end goal. I absolutely don't believe we need to understand everything about the human mind in order to build a thinking machine. I think a lot of these fascinating properties of the human mind that we see are emergent capabilities that will come about once we get some more basic mechanisms in place, and that we will come to an understanding of them by studying how they manifest themselves in the AGI system we have engineered, rather than needing to understand them but before we build something. And I think we can proceed by making AIs control virtual agents, control robots, by interacting with them and teaching them and developing the theories as we study what these artificial minds do. Now, I can't prove that any more than pessimists can prove they're right. So this is all empirical science, which is the fun of it. You can build stuff and you can see what it does. And one of the difficult things that I have learned, as so many others have learned in the history of AI, is the fact that you're building systems where all the parts depend on each other and operate together with each other. This makes it very hard to evaluate your work, because imagine you're building something with 10 components and it won't work right until all 10 of them are there and working together. And if you have only 7 of them there and working together, it's just going to work like crap. Now, in a system like that, even when you're half done, you're going to have something terrible. Analogous to once you build half a rocket, it doesn't blast off, right? So you build half your rocket, the rocket skeptic's going to say, ha ha ha, you're halfway done. Why doesn't your rocket go halfway to the moon? What's wrong with you? Of course, you can explain all you want, but if they don't buy the ideas underlying your rocket, then they'll never believe you until you're done, and the thing blasts off. So what this means is you have to be very stubborn and persistent to go ahead with building something that's so complicated and difficult that won't even do anything like what you want until you're almost done. And that may mean that we have a bad approach, because our approach is just too tangled up and all the parts depend on each other. Or that may just be the only approach. Half a brain doesn't do that much either, really. So, as you can tell, if you remove half your brain, then, well, you won't be able to tell anymore. So, we've been using OpenCog in virtual worlds. We've been using it to control this little virtual dog that builds up knowledge of what it sees in its environment. And we've been using it to control a little virtual robot that runs around in a virtual world, which has various emotional needs and various emotional demands it tries to fulfill. Now, the motivational model we use here is actually inspired by Joshua Bach's work on micropsi, although it more goes back to Dietrich Dorner's psi model that Joshua's micropsi work depends on. You have a little robot that has a need to get batteries, to get energy, and has a need to stay in his house to be safe, and has some desire to have novelty experienced as well. He runs around to get energy. When he has enough energy, he'll go hide in his house because he's afraid to go outside. Then when he gets hungry enough, he'll go out again. And these are very simplistic simulations. We've been building a more fully featured virtual world in the Unity 3D game engine, which is somewhat Minecraft-like, but not in terms of gameplay, but in the fact that it's a large work composed of many little blocks. And our robot has gotten cooler, but the new, in graphical appearance at any rate, but the new game world is still under development. The way we're developing the game here, the human player will control a little girl, and the AI controls the robot, and they're supposed to work cooperatively to do things. And hopefully next year I'll be able to come back and show you a really cool game with AI controlling it. That's still work in progress. We've learned a lot from the game AI stuff. We've learned that Joshua's motivational model or that Dietrich Dorner's motivational model, as fleshed out by Joshua, is useful for structuring actions of the virtual agent in the virtual world. We've used our probabilistic logic engine to reason about building structures. Like if the system wants to get up here, it can reason that, okay, I should build some stairs and walk up the stairs and the blocks to get on top. And we've used the Moses procedure learning engine to learn how to do simple behaviors like playing fetch or following the leader and so forth, which is videos I showed a few years ago at an AGI conference. And the next talk I'm going to give in 5 minutes, we use frequent sub-hypergraph mining, a kind of pattern mining, to recognize just common sense relationships between objects and scenes in the game world. And all that has been pretty interesting. But yet you always wonder, like, in the game world, how much are you fooling yourself? Because that game world is so simple. You kind of can build the world to show what you want to show. And sure, the AI can build stairs, get up on the table, but there's not that many things for the AI to do in that world. So the combinatorial space is not that big. So working with robots is tempting, although this video kind of shows one of the fallacies you fall into, because the virtual world here, the virtual world is almost as complicated as this world that we put the now robot in, right? So I mean, yes, it was interesting to use the AI to control this robot. On the other hand, we wound up simplifying the environment so much to work around the limitations. Now the robot could walk, and the limitations in the robot's camera eye, that really the robot's world was not any more complicated than the virtual world for the game AI. But nevertheless, we're proceeding with the robotics angle. I'm working with David Hansen. We have some funding from the Hong Kong government over the next couple of years to use the OpenCog engine to control Hansen robots, the RoboKind robots, the little guys we see on the right. And the main problem we're looking to solve over the next couple of years through this collaboration is how to glue together perception and symbolic cognition in the vision sense modality. So basically how to connect an intelligent vision system with the OpenCog's reasoning methodology. So in a way, we want to take what OpenCog is doing in the virtual world and have it do the same with a robot, but doing intelligent computer vision. And you saw little bits of similar work in Angelo Cangelosi's talk this morning, but our cognitive architecture is larger and more complex than what he was dealing with, which makes it a bit different. So the vision system we're using is written by my friend Itamar Arel. It's somewhat like Jeff Hawkins' HGM system, but I think that the mathematics works better. It's modeled loosely on the hierarchical nature of visual cortex. I mean, it's a system that has multiple layers with more and more, less and less resolution rather, as you go higher up in the hierarchy. So you have a succession of nodes at each layer, where the nodes on each layer refer to a certain spatial temporal region. As you go higher in the hierarchy, the node refers to a bigger and bigger spatial temporal region. Within each node, you have what are called centroids, which recognize a sort of dictionary of forms that can be recognized in that spatial temporal region. You could use DeSTIN in multiple ways. Itamar has largely been using it for image and event classification, a kind of classic supervised learning approach, whereas the way I'm interested in using DeSTIN is the hybrid learning approach, where we use DeSTIN as a vision hierarchy to recognize patterns in the world, and then the states in DeSTIN's pattern recognition hierarchy, those states are data mined to provide symbolic input to the symbolic system. So Itamar has done a bunch of standard tests. It gives very high accuracy on number recognition. He did letter recognition. He's done work for the New York Port Authority, recognizing different kinds of boats and trucks and so forth. Whereas what I'm interested in is that I'm interested in connecting it to a symbolic cognition engine, and that's required making significant changes in the DeSTIN architecture, which have been kind of interesting. So, for example, if you have a vision hierarchy, then you have, say, one node corresponding to a certain part on the left of your visual field, another node corresponding to a certain point on the right of your visual field. In the classic DeSTIN architecture, modeled on the visual cortex, those different nodes in the DeSTIN hierarchy corresponding to different parts of the visual field are separate. And they don't share information. You're recognizing information over here and over here. I mean, there's some interaction because there's common feedback from the cognitive levels, but they're basically separate lower level pattern recognition modules corresponding to different parts of the visual field. And that is kind of semi-biological, and that's the way Itamar did it in DeSTIN, but it makes things awkward for integrating with a symbolic cognition system. So what we did was make all the different nodes in the whole perception hierarchy share the same dictionary of visual patterns. So you basically make the whole system scale invariant, translation invariant, and rotation invariant in a low-level way that the visual cortex is not. But that if the patterns in each little part of the simulated visual cortex have the same meaning, it makes it much easier to recognize patterns like, say, an eye is often next to another eye. Because then it can automatically recognize an eye is often next to another eye where the eyes are close or where the eyes are far away, whether the eyes are to the left or whether they're to the right, and so forth. So by building these types of invariants into the visual cortex, we make it easier. So this is just a picture of our DeSTIN system, the various hierarchical levels. We can show the picture of someone's hand. As you ascend the hierarchy, you get a more and more abstracted picture of the hand. And of course, the highest level in this case is totally useless. And the level one below has a sort of abstraction of a hand-like thing with some prongs coming out of it. And as you go down lower and lower, you get less and less abstract. You have the actual hand. And what we're doing basically is taking a bunch of things like this, where a bunch means hundreds of thousands at present, millions, it'll be later. A bunch of images like this that come out of what DeSTIN sees, and mining patterns from them. And a pattern you would mine from this would be, for example, oh, there's a bunch of long, skinny things that are kind of next to each other. And by mining that kind of pattern out of all these pictures, you get more abstracted ideas that feed into the symbolic network. So what you find is using our version of DeSTIN that uses the same library of patterns on all the different scales and all the different portions of the hierarchical perception system, you need many different training examples to recognize a given object, and you can recognize a pattern like a hand or a foot or something, regardless of orientation and so forth. And one of the big lessons we've learned here is that, integrating AI algorithms is really it's not a plug-and-play operation. Even when two algorithms actually conceptually fit together really easily, you often need to rewrite the algorithm to get them to actually work together, which complicates things quite considerably. So, for part 2, this is sort of the next level up in the hierarchy. So, this is how do you mine patterns, and we're actually using this with the vision system, although this paper covers a different case. Again, we're looking at the border between perception and cognition, where I said here using pattern mining algorithms to recognize patterns in the output of subsymbolic systems. I'm going to tell you what pattern mining algorithm we're using, which takes patterns in lower level data and turns it into symbolic links in a weighted labeled hypergraph. So basically this weighted labeled hypergraph I keep alluding to, it's what I call a generalized hypergraph. So a hypergraph has n-ary links rather than binary links. What OpenCog's representation, it's a little richer. You can have links that point to links as well as nodes, which is like in relational algebra. And you can also have nodes that have little graphs living inside them, which, of course, you could map all this into a regular graph if you want to. It's really a matter of convenience, what representation you use. And, I mean, some peculiarities here are a pair or a triple of nodes or links could have a lot of different relationships between them. And time and space play a key role. So when we have timestamps on the nodes and links, and in some cases, explicit denotations of the spatial location. And time and space are important, so we pay a lot of attention to those in doing pattern recognition. So simple examples of some of the more semantically explicit nodes and links. I mean, you have an inheritance link. Goertzel is an animal, almost certainly. No. Eventually I may be a robot, but for now I'm still an animal. Right? A predicate link, say an evaluation link between a predicate node and a list. So cats often chase mice, and these are to be interpreted in a kind of probabilistic term logic, which is described in the Probabilistic Logic Networks book that I alluded to, which has some relation to Pei Wang's uncertain term logic, except he doesn't use probabilities. And basically what we do to mine patterns, it is basically greedy pattern mining, not all that different from G-span or other frequent subgraph mining algorithms. I mean, it's breadth-first greedy mining of subhypergraphs in the large hypergraph knowledge representation. We want to recognize subhypergraphs that occur very frequently in the same big hypergraph. So it could be two eyes often occur next to each other, or it could be, say, You know, I often see groups of young women walking around together through the robot lab. I mean, it's basically any frequent co-occurrences within the hypergraph, and we kind of tweak the algorithm to especially look for patterns involving spatially or temporally related nodes and links. And we work with many different quality measures. So you can look for frequent subhypergraphs. You can also look for surprising subhypergraphs using information theory, specifically a quality called the interaction information as a measure of surprisingness. So the specific experiment I'm going to show here, an earlier version of our game world, which had a bunch of kitchen stuff in it. So we had a bunch of scenes going on in this world, and there's a whole bunch of knowledge in the atom space. So in those, soccer balls are not edible, eggs are edible, chairs are often near tables, and a bunch of logical knowledge such as that. And it can mine patterns like this. So this pattern says that batteries are edible. Now that's not true for me. For this little robot in the virtual world, batteries, it considers edible because it gets power from them. So it learned that when it finds a battery, it can eat it. It can gain energy from that. And it learned that by basically trying to eat other tables, it didn't get any energy. It tried to eat a battery, it did get some energy. So by recognizing repeated patterns from multiple instances of that, it learned that it can get energy from eating a battery, therefore it's edible. Now here it learned that it's holding a battery, because it learned that whatever the entity labeled 7703 was holding a battery, which I believe that strange red thing with little claws on it, in many instances in its experience was holding a battery. It's not in that particular snapshot, but because that thing was often holding a battery, it learned a frequent pattern. Okay, that guy is often holding a battery. So just by scanning its experience in a kind of greedy pattern mining way, it learns a number of patterns in the world. And that's a more complex one, which says that if it's edible and it eats it, it will get more energy. So that's a useful thing to learn, right? If you approach something edible and eat it, you'll get more energy. And this was just a graph showing the size of patterns it recognized in this world. The algorithm got patterns conjuncting 4 or 5 things fairly often. Patterns involving fewer things were less often, just because they were less interesting to it by its interesting metric. And patterns involving more things were hard for it to find. So what we learned from this experiment, this algorithm can identify interesting patterns of arrangement and interaction between objects in the virtual world. And the next step that we're doing now is using this algorithm to recognize patterns of arrangement and interaction between things in the hierarchical temporal memory in the visual world that the robot is seeing. So the same algorithm that recognizes these simple patterns in the virtual world, we're using to recognize the more complex patterns occurring in the hierarchical temporal memory, which is just one little corner of the overall OpenCog architecture. Most of what we've done has been on the cognition side. Idemar has done the stuff on the perception side, and now one of our cognitive algorithms, one of the simpler ones, just frequent subhypergraph mining, is being used to bridge between the perception and cognition components, which is work in progress at the moment, which is being quite interesting, and hopefully next year we can show you dramatic results from this, but we shall see. And now the next talk, which Ray-Ting will give, will describe yet another component of OpenCog, which is to do with natural language processing, a different kind of input. How do you get English language in and out of the OpenCog system?
Ray-Ting is from the University of Xiamen.